All right, is it all good? Everyone see it?
Yeah.
Cool. All right, so hello everyone. My name is Baker Kuehl. I was a PhD in Eric Cochran's research group, and I graduated in 2022. And then I joined on as a postdoc because I actually was a part of two startups. One called Soil Innovations, which we do proprietary or basically ISU patented asphalt technology to help prevent potholes is basically the idea. We did about $500,000 worth of revenue this past year, so we're pretty excited about that. I did a lot of the technological development on that. And then the company that I've been pitching, I'm more of the business role. So I act as the CEO, and that's called SABER Chemical. And that's kind of the idea behind this presentation today is talk about the journey from that all the way to how I became the CEO and kind of the differences between, the technology and how developing it from Iowa State all the way to getting an actual pitch deck where you're really just talking about the business side. And so my colleague Vivek Garg, he's also co-founder of Saber Chemical. He recently did his prelim, and this I took some slides from him. He really helped expand the technology that I had started during my PhD, and he was a big help in kind of developing Saber's technological roadmap. And so this his thesis is next generation polymer bioplastics. This is some of the undergrads that worked on it. And the whole idea is that, plastics are basically ubiquitous to our society. However, bioplastics just make up a small percentage of that. And the reason for that is because, a lot of them are incredibly brittle. Yeah, they're biodegradable, but to, translate them to marketplace, they got to act like, the incumbents. And so PLA is basically the most important bioplastic in terms of volume and price. It's the highest volume uh, bioplastic, and its price is about 30% more than PET. So you have a 30% upcharge. But one of the big issues with it is that it's extremely brittle. And so normally durable engineering thermoplastics like ABS, polyethylene, they have high toughness, high negation, and high impact resistance that actually make them useful into the applications like food packaging, automotive, medical, all those kinds of different applications. And so what we had done on the Iowa State side, so I had started this during my PhD and I've really expanded on it, was this idea of these core shell polymers. And so the idea of a core shell polymer is that, the core is a rubber, and, incumbents are all these petroleum-based core shell polymers. But when you add them into these bioplastics, they actually and while you can toughen the material, it actually just ends up generating more microplastics. And so that's kind of the whole idea of what my part of my PhD and Vivek's PhD is doing is making it so that these core shell polymers can actually improve the durability of bioplastics without actually generating the microplastics. And so the idea is, the core provides the rubber, that dissipates the energy, and then the functional shell. So polymers don't like to mix. The functional shell have graft to the PLA matrix, reducing that interfacial tension and actually getting it so you can disperse these particles and get the really great mechanical performance that you're looking for in these engineering plastics. And so how are we doing this? Well, Vivek, once again, he actually developed, him and Michael Forrester, they worked really hard together to develop a process to convert crude glycerol into socatal acrylate via continuous process. And so interesting enough, BASF has actually tried making this monomer, and their process takes about 15 hours. And we were able to boil that down to about 15 to 30 minutes with a continuous process. So we can make acrylic monomers, at incredible volumes and incredible speeds with really great throughputs. And so how we end up making these particles is through a seeded emulsion polymerization. So you can imagine taking the monomer from our brown bottom flask, and then basically turning it into a core shell polymer latex. So we make polymer seeds and then grow our particles to about 320 nanometers. And then we use extrusion to basically blend these particles to end up getting our modified material. And so just a bit of how emulsion polymerization works. You have these monomer droplets forming from surfactants, and then you have your water-soluble initiators. And so these water-soluble initiators basically find the monomer, the small amount of monomer that's soluble in the water phase. They form oligomers as they react, and then they form these micelles, which then basically grow to your monomer swollen droplets, and then yeah, you get these polymers essentially. And what's really nice about emulsion polymerization is your water is your solvent, so obviously that's low VOC, excellent heat management, very scalable. So you can think about paints, coatings, current petroleum impact monitors all really synthesize this. You get really high molecular weights, and really high conversions as well. One thing that we've kind of noticed is, yeah, by the end of our polymerization, there's just no smell of any monomer left, which is kind of cool. This is an image of just our polymer latex. So you get this nice white milky, nice white milky latex. And so how do we synthesize it? Yeah, we start with a core. That's basically our rubber. We polymerize our shell off of it, and we get a functional shell. The particle number throughout the polymerization can't change. The reason for that is because if you nucleate new particles, I don't know if when I originally did it, and I taught emulsion polymerization myself. If you spray dry rubber, I can tell you it's an awful process. It doesn't work very well and can create a huge mess. So you really need that shell on there to actually get a nice powder. And so once we, effectively tuned our critical micelle concentration below, or surfactant amount below the critical micelle concentration, and we really expanded out how like some of these ideas that Vivek found, less than 3% monomer in the aqueous phase, the whole CMC, low amounts of radical flux, you can really get it so that the amount of monomer that's affected, or the amount of monomer polymerizing won't actually generate new particles, and you get these really fine tailored core shell particles, which is really important so that you don't clog your spray dryer. And so this is just kind of actually the images. So this is some of the stuff I had made originally on the left. So it doesn't have shell coverage. You basically get this nice, not nice, but very clumped particles, and it's just terrible. But when you have shell coverage, you get this really fine powder, kind of like flour. In fact, if it like out of the spray dryer, if you can get it really fine, it actually aerosolizes in the air. So we actually wear masks for it. But that's really nice for extrusion because it really helps with dispersion. And so after spray drying, when it has nice shells, you can really see the really fine powder. And yeah, at the bottom we have a table just of our core shell, functional shell sizes, and we really tailored the shell size and found that shell percent was important, and then the pH was important. So really neutralizing to get the shell to actually polymerize off was important, is what we found. And then just validating. So we've made petroleum incumbents, we've made 50-50, made 100%. We're slowly trying to scale these up so that we can actually do real trials with them with companies like Lystridge that we've kind of found that are really great to work with in terms of getting some initial demos done. And so that's basically an idea of how we start on the Iowa State side. However, when you get to be a company, you have this technology, and you really have to figure out, okay, well, what pain points am I really kind of addressing, and what are some of my markets that we're really looking at? And that was very different for me because I basically spent all my life as a technical person, and so really learning the business side was a big shock and a big change for me. And that's really where I've kind of grown as an individual. I've got the technical side really figured out, and I've been trying to learn the business side. And so we took the technology. We got an NSF I-Core grant. And so they were kind enough to sponsor about 50K. So we could basically do the whole customer discovery process, which was really important for us to really know what kind of markets we go after. And we could basically spend, I don't know, what was it, 4 months kind of doing that. So we conducted a lot of interviews. We did about 113. Trade shows were very different than like technical ACS conferences. So the amount of stuff that was there, like there was live music, open bar. It was such a different experience, but it was a lot of fun, honestly. We had 62 in-person calls, 49 virtual. But we really wanted to validate the technology. And one thing that I was not used to was pivoting. So when you think about it, you have a technology, and you get it so that you think it's the next best thing since sliced bread. And so when you go to interview people, and you end up trying to fit a square peg in a round hole, and that's kind of what we start with. So Vivek and I would be up till about 1 a.m. doing our business model canvas and really trying to figure out what our beachhead market was. This is just kind of an image of me just frustrated, but I kept persevering. So by week 4, we really started to get an idea of where we could start. So, we had conversations with Orobio, and they're kind of a PHA company. They explained that PHA was really brittle. They were looking to fix that. In the 3D printing space, we found that we validated one of the pain points, that PLA also is even more brittle than it already is with 3D printing. And so Simon, he at 3D Actions, PLA for him was very, he could only use it for his figurines. And so he really was looking for, and like ABS and polycarbonate are really, they have high durability, but they're a little hot. They're more difficult to print than than PLA, and he was looking for something that he could use as a prototyping resin that matched the durability without having the difficulty to print to some of those other resins. And so that was pretty exciting for us because that was one of the pain points that we felt that we could, address. And as I said, we went to multiple trade shows. So on the left, this was a guy who was from an extruder company. So I learned a lot about extrusion. On the right, I was as sick as a dog. I mean, we had been traveling and staying up and doing business model canvases for, basically 3 straight weeks, and I got sick, but I kept persevering because we know we needed to find out that information. And so that was actually at like a meet and greet, and we met quite a few people there. But one of our biggest interviews was actually Charlie Martin from Leistrich, and Leistrich works really well with startup companies, which was really important for us because, as I'll show later in my slide deck, that we basically got $20,000 worth of value for $500. And as a startup, when you don't have a lot of resources, those are incredible partnerships to really have. And so that was basically what we found from that was basically our best finding besides the pain points for iCore was just that connection. And we've really developed our ecosystem so that we've got multiple trials set up where we have an injection molding trial where, once again, it's $20,000 worth of value for basically free. So that's really important for us. And now I'll kind of transition into SABER Chemical. This is actually a technical deck. So I put together two. I've kind of conglomerated a bunch of presentations together. Um, and so this will be our tech deck, which was different than we've learned how to summarize technology for non-enabling so that, somebody off the street can really kind of understand the technology. And then I'll have the pitch that I gave at Iowa Bio. Really, that's kind of how I've transitioned my role is, I know the technology, but really being able to kind of speak it in terms of business is what I've really learned. And so where SABER's at now, our long-term objectives are, food packaging, films like trash bags, paper coatings for yogurt, bottles, and then sports manufacturing as well. Our current beachhead markets that we've really found through iCore, which was 3D printing, and then the sports manufacturing where we're doing golf tees and pickleballs. And so, the performance requirements in kind of these spaces. So the PGA is really looking for, golf tees that are durable but compostable. We've had pickleball companies reach out to us for that kind of same idea. They have professional players that are where they're playing with these pickleballs. And so we're having partnerships with that. And then 3D printing, we're currently sampling that as well. But the performance requirements, degradable, needs to be durable. One of the big issues, the pain points that we kind of saw was, bioplastics are brittle. And if you want, you can't really just do, the whole idea of it just being green and being important really isn't, you can't do that. You can't really do that anymore. That's just not going to suffice. And so the performance has to be there as well. And so, and then our current priorities, finding tollers. We're really looking to scale our products as well as, we're actually forming an advisory board right now. As I said, I've been only doing this for, I don't know, 3 years now, 4 years for all my different startups. And having people with 30+ years of experience develop, taking products to lab scale to make actual products, and then understanding the global market of plastics has been really important. So, I'd say in the next month or two, we'll be finalizing our advisory board. So what do we offer today? We offer high performance 3D printer filament. We actually have tested this 3D printer filament. We've made pickleballs. So actually, I can hold one up. We've made little pickleballs, which has been really cool. We've made just a bunch of different objects, even test tubes actually for culture for cell cultures. We found that this 3D printer filament basically has the same impact strength as polycarbonate. So it's even probably over-engineered, which is kind of cool because then we can actually lower our COGS. And we also recently did a golf tee trial where our golf tees have survived so far 2 full rounds of golf, so 36 holes without breaking. And so one tee is just surviving, is basically going to survive the whole summer, which I think is pretty cool for a bioplastic. With SABER Orange, so Leistrich really helped us out with that and how we manufacture. One thing that's different from SaaS to hard tech companies actually have a big CapEx. And so you can't really just go out. There's like a chicken or an egg kind of problem where you need money to actually manufacture things. Then it's a huge CapEx. So how we're kind of doing it right now is we're actually tolling our extrusion in consumer goods. And we've really kind of just now become a whole kind of sales and marketing company currently. But if we get to the certain point where as we scale that we need to bring our own manufacturing, that's something that we also are interested in. But as of now, we're just doing our tolling. And so what exactly is SaberFlex 1101? And so this is kind of the difference between, something you do at Iowa State versus, a non-annealing pitch deck is, you know, how does it boil down to like the bare bones? And so what exactly it's an alloy of PLA. And then rather going to like, the cold shell polymer technology, the core shell, the size, blah, blah, blah. They don't really care about that. They're interested in, what does it do? And so it's more compostable than PLA, where we have through customer discovery, we actually found Mississippi Polymer Institute is willing to do compostability studies for us for free. That's normally 50K. They currently are trying to become BPI certified, and so they have a grant that's basically paying for us to actually test our materials, which we're really excited about because yeah, normally compostability testing is 50K. And as a startup, you don't have those resources. So we're actually expecting marine compostable anticipated, and I know Vivek's working on some new additives that it can be incorporated for get the back air compostability. And so this is kind of a video. This is actually a Lystrich. They actually did the 3D printing filament for us. So as you can see, they're winding it, and it's really cool. We were really happy about that. And so how does it compare for, traditional PLA versus SaberFlex? So traditionally on the left, you have normal PLA, extremely brittle. When you hit it, when you do an eyes-out impact test, it just totally shatters. And so what does SaberFlex 1101 do? When you do a tensile test, as you can see, it's pulling it up, pulling it apart, and you get, a nice, really tensile elongation. And then when you do your eyes-out impact test, the hammer's going back and forth, and it's just not breaking, which is pretty cool. So that really, shows the durability of the product. And the really cool thing about SaberFlex 1101 is just by tuning crystallinity, you can change its properties dramatically. So you can imagine for amorphous, you can get really nice strain of break, really good films uh, that you can turn into for packaging. And then for the crystalline, you have then durable goods for automotive applications, food containers. Obviously, we need to go through food contact safety, which is ultimately why we pivoted away from food to start into it just wasn't a very great beachhead market to do, but it's obviously part of our long-term plan. But we can't really start there with the resources that we have. But so this is kind of the bare bones of properties that people kind of wanted to know. So it's basically what's on our technical data sheet. But I just thought it was really interesting to highlight that we can go into both flexible packaging and durables just by changing the crystallinity of the final product. And so how does it compare against, some other polymers out there? So against ABS, it's basically, so general grade ABS around 200 joules per meter notch size on impact strength. And, some of the high impact automotive grades are 400. And so we're actually showing that we're directly competing with ABS in terms of, the high impact strength grades. And then, PHA, this bioplastic that's fully back compostable is, just incredibly brittle. And so we believe that, it's blowing PHA from a mechanical performance standpoint out of the water. And then, we believe that it's going to get to marine degradability with our current formulation. And then just by adding in some new additives that we're planning on, doing for basically our 1102, SaberFlex 1102 product, that we can basically achieve a fully back air compostable product that meets ABS properties while, meeting the same back air compostability criteria that PHA has. So this is just a video of our 3D printer settings, or some of our 3D printer settings, and a video of we did a 3D printer test, and then we wanted to make sure that we wanted to test the durability. So injection molded parts are great because you don't have any, there's no interface between the layers. It's all just one cohesive thing. However, there's the 3D printer, you get layers, and so that causes defects. And we wanted to make sure that when you pull on those layers that you actually get the durability. And that's a tensile bar. We did notch eyes at impact strength as well. And it really shows that even our 3D printed part has really great ductility and durability. So future technology, as I mentioned, at the moment we are looking to at the moment, we have our beachhead markets where it's, sports manufacturing, 3D printing. In the future, we want to go into paper coatings, food packaging. Those are high volume markets that, our investors have really told us that we're kind of going after, that's kind of where we need to hit. They're okay with beach markets now, but they really want to see that those large markets entered, and that, because they're looking for, the 50x, 100x return. Vivek and Michael really worked really hard. So a bio-based monomer slash even just conventional acrylics system where we can make really high volumes of monomer. We think that's going to be a really big disruptor in the marketplace in terms of current acrylic monomer production. However, big capex. We need to demonstrate that as a startup that we can make revenue before we go after something like a Series A, where that's technology we can go after. We got core shell polymers, so rather than for not just PLA, but core shell polymers for all different kinds of matrices. So like PBT, PVC, PMMA, those kind of matrices. Polymer latexes as well. So we've done another Iowa State project, interesting enough, was a powder coating with Sherwin-Williams. We got to a point where they were really interested in the product, and they wanted 100,000 pounds of sample. Well, obviously we can't front that for cash, nor did we have the production to do that. So that's another promising future technology that we eventually want to achieve. And that's because it's kind of our commercialization roadmap. We're starting with SaberFlex Low 1 into the 3D printing sporting goods markets. Then we'll basically continue to launch these different technologies as we raise the necessary capital. This just goes into a bit about the next generation monomer synthesis as a continuous process, high throughput. It's basically 5 times the less energy consumption that BASF's process has. That's for traditional transesterification. And it's not just silk catalytic; it encompasses all those different kinds of acrylic and methacrylic monomers. This is just a team of some of our coatings that we've done, or well, the latex, and then so we've kind of done coatings. So aqueous blends, you can think of impact modifiers, powder coatings, architecture coatings for all these different reactive core shell polymers. And then we've even found that our petroleum impact modifier is interesting enough. We've really gotten so good at emulsion polymerization, we can make these reactive core shell polymers that really aren't well developed in the marketplace. And we've seen that we can get notch diazide impact strengths really great with those as well, and in those different kinds of matrices, which we found is pretty cool. Normally, conventionally, they have to incorporate basically this massive formulation of 4 different polymers, and we've got it down to 2, which we thought was pretty impressive. This is ultimately the biotech pitch that I gave. It's a very different, obviously, it's a business, so I'll kind of talk about the differences between that. I'll go through each slide. So the plastic paradox, plastics are ubiquitous. The U.S. alone produces 100 trillion pounds of plastic globally, or 100 trillion pounds of plastic annually, to supply markets range from automotive parts, medical supplies, cutlery. Interesting enough, I don't know if everyone's familiar with this. 20 years ago, you were consuming over a credit card per week of plastic, and over your lifetime, you can actually expect to just store 2 trash bags with plastic. Microplastics have also seen they're pretty big in the news right now. I don't know if people have kind of the health organization has come out and said that that's one thing they're kind of studying, and they are trying to kind of link potentially some of the different diseases with the idea of microplastics being in our bodies. And then, as I mentioned, I've shown that companies have tried shifting to compostable plastic, but they're just too brittle for real world applications and require need to require real world strength to actually be useful. And so, what is our solution? So we have an elite performance solution where we actually have durability of product. Our product is durable. We also have the freedom to operate via an exclusive agreement compared to our competition, which too weak, too brittle, includes toxic additives. What's the competitive landscape look like? Dow and Canica, they really offer great durability and performance, but they lack compostability. Natrix and CJ Bio really offer biodegradability, but low performance. And we find that we really stand alone in terms of this. So we actually make it so the user doesn't need to make that choice between performance or biodegradability. They can realistically have both, which we've really seen as our difference in how SABER can be a disruptor in the marketplace. Then, what's our market opportunity? The whole plastics market is worth about $580 billion, and nearly 50 billion of that requires strong and durable plastic. The food packaging industry is worth hundreds of millions of dollars. But as I mentioned, it's not a beachhead market because it requires long development times and high capital cost. And so we've really started and tailored our initial products to the sports manufacturing 3D printing space, where those markets are worth around $1 billion, and we can generate early revenue without needing to invest in new capital or R&D. But eventually the food packaging is part of a long-term plan. But yeah, we're starting with this as a beachhead market. And this is where this is one of my most important slides. Why I will say customer discovery is basically the most important thing ever. Is with LifeStreet, we did a $20,000 project for only $500. And when you're a startup and you have no money, $500 is a lot easier to swallow, lot smaller pill to swallow than 20 grand. And so we basically got $20,000 worth of value, and we're using these materials to supply, 3D printer influencers as well as the PGA Tour and professional pickleball players to really gain that publicity that we're looking for to bootstrap the company to start to get investors interested and to invest money into SABER. So what's our business model look like? Today we're at the precipice of, selling into B2B and B2C markets in the performance sporting goods and 3D printer filament spaces. As we scale and get, some initial investment, we're planning on selling raw materials to plastic manufacturers, as well as begin selling into the food packaging space. And then the investors always have, especially the IO investors, have this big phrase where they want to shoot the moon, and our ultimate moonshot is that we are partnering with some of these big Goliaths like PepsiCo, BASF, and Amazon to become the world's leading choice in bioplastic we can ultimately live with. So bioplastic that are degradable, as well as have that durability aspect that we found is an important pain point. What's our team look like? We have a bunch of technology people. So I'm currently the CEO, acting as the CEO of Vex, currently acting as the CTO. Eric's great because he has like some legal experience with doing a lot of some patent publications for to help with iSurf, and then Michael's really great at coordinating all these different trials. I have 5 email inboxes now, so it's just really great to have him on the team because he's really good at that kind of stuff. We're, like I said, we are in the initial stages or final stages of forming an advisory board. We're adding people with 30 plus years of business experience, as well as talking with some other founders in this ecosystem that we think could really help, that have different aspects for each one of these founders that can really help propel them forward into these roles as an advisory board member. One of the most important things so this isn't quite an investment pitch. This is more just an actual pitch. I'm working on an investment pitch now that I'm working through with Ag Startup Engine. The last thing you always need is basically an ask. And so, for instance, this pitch that I did, this pitch that I did was a 10K pitch. And so I was planning on using the 10K for the compostability studies, as well as to buy some material for our trial that we're planning on doing. I really demonstrated that we've really been able to be good at taking money that we've been given and turning that into more value. So for instance, I got 5th out of 60 in the Papa John's pitch competition back in August, and we turned we turned that $5,000 into the $20,000, or $500 to $5,000 for the $20,000 worth of value that we've really used to be able to bootstrap SABER, unlock its opportunities in this Iowa ecosystem and the startup ecosystem that we're really utilizing. So that's the full kind of how my journey's been from the Iowa State side as a researcher all the way to developing this business pitch. And then there's more to come. I'll be doing an actual investment pitch that I've been working on. It's not quite done yet, which is why I didn't put it into this pitch comp or this presentation. It's a lot like this pitch with a few different aspects. So with your cost of goods and a few other things that they were looking at that I'll have to put together. But yeah, it's been an exciting process, and definitely I've learned a lot, and yeah, hopefully continue growing and getting some investment to really get this stuff out here and take the technology out of Iowa State and get it into a startup that can really be a disruptor in the marketplace. And then yeah, I'll be happy to take any questions.
Thank you, Baker, for your presentation. So please let him know what you have in mind, guys.
Yes.
Yeah, this may seem like a silly question. It's really just curiosity. The orange color, did you add that intentionally for some sort of a marketing reason? Because it doesn't seem like the type of orange that would come from your original chemical process.
Correct. So we added pigment into the extrusion process. You know, white is great, but for 3D printer filament, it's typically colored, and so that's one of the initial beachhead marks we want to go through. The other thing is what we wanted to confirm on the trial is, can it be colored? So there are certain resins actually don't take pigment very well, and that's one thing for 3D printing. That's, you know, I don't know if you're familiar with 3D printers, but they come in all different colors, like holographic colors, shiny colors, blue, red, green, magenta, forest green, like just all these different colors. And we needed to prove out if we could actually color, because that'd be a big problem if we couldn't get it to color. And yeah, with very little colorant, it looks fantastic. So that's why it's not from the product. The actual resin is white. We colored it using pigment.
And all of the material is orange right now because you did that one large batch. So you did one color, right?
So our 3D printer filament is orange, because and then our actual pellets we kept white. We knew that, so if we had somebody call up and be like, hey, we don't necessarily want orange, we want to pigment it ourselves, we kept some stuff white just so if they wanted to take it and sample it, they can pigment it whatever color they wanted to. So we strategically did kill two birds with one stone. We made sure, you know, some of it was white so that we could not have to worry about people complaining about it being orange, and then also having orange so that we could make sure from a technical perspective that it could actually take color in.
Thanks.
I'll ask a question if no one else has one. Baker, do you know what the the degradation products will be upon composting? Do you know? Do you have models or other things to know exactly what will be there when it's, you know, been composted?
So that's kind of why we're going to do this compostability, but we definitely think that one will be glycerol. That's definitely for certain.
Yeah.
And then, you know, probably CO2 as well. And then the whole idea is that we're really tuning basically so that when you get to that polyacrylic acid chain, that it breaks down as well. That's one of the biggest challenges with acrylics. That's one thing we've
and that's what shot up to me. I was like, do you know of the? Yeah, I just am. You know, my vague recollection is that the polyacrylic acid is not compostable.
And currently, so the way it works, we really tune the cross-link density of the actual polymer so that it's below, so it provides that toughness and durability without being too brittle. Obviously when you cross-link something too much, it becomes brittle. But the way polyacrylic acid works is there's a certain threshold of molecular weight between cross-links where it actually those little bugs will actually chomp on the polyacrylic acid and turn it into and actually degrade it. Interesting enough. There's some literature precedents out there, and we're going to be testing that in July.
Yeah, no, as I said, Jessica, that's why I was curious if there was some known mechanisms outside of that, because I mean, as a teacher of organic chemistry, I can tell you that I know that there are ways to contrive to make those carbon-carbon bonds weaker to be able to degrade them. But again, I do everything in a lab in a flask. I'm not a bug that goes and does it, so I don't know what biochemical processes you have access to that could do that in like a home compost or something like that.
Well, in July, that's exactly what we're going to be testing. So
cool.
Yeah,
I'll look forward to that. Thanks.
Yep.
Other questions? Anyone?
Yes.
Yeah, hi Baker. So I'm wondering if you have strategies that you can use for really varying the density of these core structures that you have. Right now, it looks like it changes from 1.1 to 1.2 on your one slide. I'm just wondering if you wanted to have a density of, let's say, 3. Could that be done with different materials, perhaps with the core material?
So one thing that's so Dow Chemical actually has what's known as a hollow core shell polymer, and interesting enough, you can take those particles, and since it's hollow, it basically has air around it, and I know you can drop the density. I know you can also get it so that you encapsulate, pigments and other metal particles that you could probably actually use to increase the density. I don't know much about increasing density. I do know when you make hollow core shell polymers, you can drop the density significantly to like 0.4 or something like that. I think is what Dow says that their density of their particles is. I'm not as familiar getting it to 3, but yeah, I'm pretty familiar with lowering it.
Okay, guys. Laura, any questions? You always have questions. No, not this
Oh,
time.
no, it was a really interesting talk, and congrats on all of your successes. So, and thank you for taking the time to tell us about it.
Yeah, thank you for having me.
It's always nice to see one of our graduates do well.
Appreciate it.
Absolutely. Okay, thank you, everyone. Thank you, Baker, for your time, and have a great rest of your afternoon. See you soon.
You too.
Bye.
Yep. Bye.
Hi, everyone.
Bye.